Hello and welcome to week 4. So this lecture is going to be probably over an hour. That brings me to my first question. Do you prefer shorter videos, 2 or 3 of them, or one longer video? In the past, students have preferred longer video because they can pause it and just remember the time. But if you prefer a different format, just let me know. So this week's more the grammar of what machine learning models use to understand the world. We'll be covering chapter 1 and chapter 2 in this book. But again, if you don't have this book and you want to use different resources, that's totally fine. And I'm expecting you to go out and kind of do some research on your own. These 2 chapters aren't particularly big, but they encompass a lot of information. I mean, you could have a whole class in these 2 chapters alone. So if you're interested in part of the talk, Google it, or I can try to help you find additional resources. The book goes in this particular order. And some of them, like, the moving definition of a large language model, the year of generative AI, open source models versus like closed source models. Chapter 2, tokenization and embedding. Like I said, these could all easily be a whole semester course. So I love this quote: machine intelligence is the last invention that humanity will ever need to make. Because in theory, if we get to AGI or we get to some type of singularity or machine that can grow, adapt, and think on its own, it can help us solve problems together in partnership. And this is kind of what I mean in partnership. So humans and AI, like I said, from what I understand of how this process works, humans and AI discovered a whole new class of antibiotics. And antibiotic sales is a $50 billion a year market. So I guess the way that this happened is the AI would kind of come up with some ideas, humans would model it out or test it in the lab, and then get the results to AI, and then AI would come up with more ideas and go back and forth. And this back and forth process, this teamwork or synergy, allowed us to create a new class of antibiotics, which is amazing. So I think we'll be seeing a lot more of that in the future. So the book goes into a little bit of the different types or the history of AI and LLMs. And I will tell you that LLMs and ChatGPT and Claude and Gemini and all the models and all the machine learning are accelerating so fast, it's very hard to keep up with it. I mean, I work on this stuff all the time, every day, and it's still hard for me to keep up on it. This morning, one of my coworkers emailed me, "Hey, look, this is coming out this week. This is coming." I mean, it was probably 10 items of new models, new developments, new software that's coming out. This is just one week. And you have a lot of Chinese companies releasing new models. It's very, very competitive market and very innovative market. Now that's good because that pressure to create something new helps drive LLMs, helps drive large language models, helps drive innovation. The problem is also, if we're not careful, if we push too hard, we might create something that's not beneficial to humans. So this is something I go over when I speak in large public events. And it's so hard because all these terms get mixed up by the media. Sometimes I mix them up. And when we say, hey, what is artificial intelligence? What is machine learning? What's deep learning? These terms are kind of flexible. So this is something I found online, and I just kind of like this chart. So artificial intelligence, it's not real intelligence. It's simple AI checker, uh, maybe even linear regression. Things like this are artificial intelligence. From that, we can kind of drill down to machine learning. And machine learning says, hey, if we have this data, we might be able to predict that data. If we have this might happen. And deep learning goes even deeper than that. And it says, hey, if we have this data and this happened, and we have this data and this happened, there's a pattern. We build up from our predictions into deep learning. Finally, generative AI. This is, again, one of those really kind of nebulous terms, but generative AI is when the machine moves away from finding patterns to creating pattern, to creating scriptive information. So it can be, in my example, creating a real looking X-ray. It can be creating real text. It can be coming up with a new class of antibiotics. But at the end of the day, it is creating new text and images and code to help solve the problem. And continuing on this, we have a biological neuron on the bottom left and a computational neuron on the top right, and vice versa on the right. I guess that's somewhere I messed up. But anyways, though, and you see that they're very, very, very similar. I can get in here just a little closer. They both receive input. They both weigh certain inputs in order to get an activation. And with both biological weights and with computational, or with biological neurons, the computational neurons, weights are learned or trained. It's a parameter. In our brain cell, our brains fire when we have a strong enough signal, something we've trained it to fire on. Artificial neurons do the same thing. Now, I'm not going to go too much into detail on that, but there's a lot of similarities and in some ways a lot of differences. But for the high level overview of this class, they're very, very similar. Now, with the way AI and machine learning is done, it is a fundamentally different process than traditional programming. If you look on, I don't know, TikTok, YouTube, you'll see videos on, my kid wrote out instructions on how to make a peanut butter and jelly sandwich. And then the dad will try it and it just gets totally messed up. And so that's how traditional programming is. You have a bunch of data, or data, not a bunch of data. You have rules. And you just kind of take that out and follow rules, data, rules, data, rules. Well, the problem is, in such a complex world, we can't always enumerate all the rules effectively. And you'll see that with that, I think it's like a peanut butter and jelly sandwich or something with a kid. Um, this is where kind of one of the first paradigm shifts of how machine learning works. We give it the data just like we do with traditional programming. However, we give it examples of output. And we say, you make up the rules. Here's the data we have, and here's kind of what we want. We'll train the weights. You have to figure out how to come up with rules to make the data look like the output. So it's a fundamentally different process in traditional programming. So large language models, that's what started a lot of this. It's the ChatGPT, it's a Llama, it's Claude. Um, they don't understand context like humans do, but they're very, very good at recognizing patterns and responding to based on what they've read or the patterns they know. So traditional AI analyzes data to give predictions. If X, then Y. Generative AI can kind of make new patterns and make new assumptions. It can write in a more attentive space. So, LLMs recognize patterns, but they really don't understand the same as humans do. Or, again, traditional AI it's just predictions. This is another neuron one because often we see one neuron or one weight, and that's just part of the equation. This whole artificial neuron would maybe be here. And then this one will link up to this one, and this one, and this one, and these link up to these. We had millions of these together. We had billions of these together, and now models can become functional. Now, what led us here? How did we get here? Well, one of the, and I don't know what book this is from, but one of the ideas is that, actually, let me fix that, is that when we moved from analog storage to digital storage, the way information can be changed is much easier. Let me give you an easy example. So I have an MP3 and a record. How do I copy a record? I don't know. I can't copy a record. I mean, I have a 3D printer. I still can't copy a record. How do you copy a record? It's quite hard. And we have a VHS tape on the screen. How do you copy VHS tape? Well, with a VHS tape, you have to have one, I guess, VCR and another VCR, put one in, hit play, go all the way out to record, and it takes an hour to copy. Well, let's think about it. With an MP3, I can just copy and paste. And I literally 3 seconds. I copy an MP3. So if I have 10, well, let's say I have this audio recording in my class. I want to give a copy to all the students, all 70 students, and it's on VHS. That's 70 hours of copying and pasting, or sorry, of like hitting VCR tape in, hitting play, and hitting record. If I have 2 VCRs, that's 70 hours worth of work. If I have my class on MP4 or MP3, I can just take it, copy, paste it. I can do that 70 times. I'll be done in less than a minute. I email all of you. You have copies of it on your machine, and you email your friends, and we get this data explosion because now digital data is a lot easier to duplicate. And so this information is growing at such a rapid pace, it's hard to keep up with it. And that is why machine learning, AI, LLMs are so vital, because now we can finally start processing this raw storage that we have. We can finally start processing and understanding some of the knowledge that we have. Now, before we go too deep into this, I want to understand just 10,000 foot overview. How do we teach a child to understand the world? I, you know, I don't have any kids, but if you think about it, you say they're removing a sound, cat, cat, a cat. You can kind of teach a child parts of a word and then combine them together. You can map sounds to words. This is why I suck at English. I don't have a problem with this. You can break a word up. You can call this tokenization machine learning. Banana. So if you kind of think for a second, how humans teach other humans to communicate. This will be beneficial when we go to teach you how machines learn how to understand and communicate. Now, I've never figured out really the best way to explain everything. I mean, sort of having 900 slides, and this is already 46 slides. Um, so what I do is I just kind of, I think I have 3 or 4 pages of terms. I'm just going to talk about them, go into detail after these 3 slides or 4 slides, a little bit more in detail on some of the key terms. But in my opinion, these are some of the most important terms that you can understand in order to really get an understanding of how ChatGPT works, how we take our language and our text and make sure a machine can understand it. Okay, so I'm trying to catch up on my iPad. So if we look, I like it better on the screen, but where's my iPad? There, look at that. Okay, so we have covered already AI. Um, so for natural language processing, for this, and the way I kind of split up part is kind of LLMs and then before natural language processing. So on your discussion post, I have some just natural language processing. It tells me how many words you did, how many links you posted, just real basic stuff. So that was kind of before LLMs. Now, LLMs nowadays can take what you post and summarize it. I'm not doing that, but it could. So, in my kind of idea in the world, there is LLMs versus just traditional NLP. Okay, what's an L? Um, like I said, this is a Chat GPT, Claude, whatever you use. This is other tools. It's Space Shape, Space CY, and tools that would basically we're going to talk about, and then that you're going to use it kind of can stem a word, can group words, can convert them into numbers. So when people talk about this, just make sure you know that if they're talking about an LLM like ChatGPT or they're talking about traditional NLP. Yeah, sorry about that. It's okay, some bag of words. So bag of words is a very, and your book has a definition, and I think I have a picture of it in a couple slides. But basically, it's just when I grab every word in a paragraph or a page or whatever, and literally just put all the words together. So if there's 3 there's 3 If there's 10 A's, there's 10 A's. If there's the word bag 2 times, bag's there. Okay. And tokenization is the process of splitting text into smaller units. Okay. Now, those units can be sentences, they can be words, they can be characters, they can be a lot of different things. But tokenization is just taking really, it's I think do this. It's taking text, like that, and figuring out how we're going to break this part and this part into 2 different words or to 2 different tokens. Humans do the same thing. In our mind, we do the same thing. If you see the word unhappy, we don't really process unhappy as a whole word. We process happy and then we tokenize it. And for those of you who take a psychology, this is a priming effect. If I give you the word teacher and then show you the word teach, I've primed you. I pre-tokenized you, which are weird terms. Now, corpus is just a collection of words, documents. It's an entire catalog. Vocabulary, that is okay. Dense vector encoding. There's a couple different encoding methods, and what do I mean by that? I don't know if I like that definition. And I have a video on an animation on dense vector encoding versus sparse encoding. But at the end of the day, it's kind of how many neurons fire when information comes in. I guess that's the easiest way to think about it. There's a couple different types of models. There's decoder only models and encoder only models, and both. There's a encoder with autoregression. There's a couple different types of models. For now, we're not going to go into too much detail related to that, but just keep that in the back of your mind. Word to vec is a method where I can take a word, Richard, and convert it to a number. Now, why do I want to do this? Because it learns from other words around it, kinda. Um, because I know that if I convert this to a number and I have the word Richard misspelled, a D, I convert that into a number. Hopefully, these two numbers are going to be close to each other. But we kind of lose context out on this too, that we don't really retain semantic information. So quantization. Yeah. So this is the idea that when we design a neural network, we can track to a certain percentage of accuracy. However, for most of the time, we don't need this high level of accuracy. The analogy I make is if I said, "Hey, let's all meet at In and Out," okay, and I'm like, I don't know the address, but I can give you the GPS coordinates. But if I give you the GPS coordinates to like 100 places, or even 32 places, by y. I mean, that might be the actual spot on the door handle. I mean, it's so accurate. It is just wasteful. Where in reality, I can say, hey, just meet me at this location, or even even cut it down some, you know, and when I truncate it, I might lose some accuracy, but for the most part, that juice is worth the squeeze. The squeeze is worth the juice, whatever that saying is. Um, Meaning that I've compressed it down so much that I can't really tell a difference, and it just runs faster. I can use it on my computer. I can use it on every device because I quantized it. And I mean, so we look at DeepSeek, which I think was on the last slide. I think DeepSeek is about 700, you need about 700 gigs of VRAM, which nobody has. Even if you have like 4090, you really can't run DeepSeek. However, if you quantize it, well, you can quantize it and get it down to a small enough thing. Now you can run DeepSeek on a relatively large personal computer. So you can't run the full model, but you run the quantized version of it. And it's 99.99% just as good. Hugging Face is, like I said, the best way to I explain it's kind of like a GitHub for AI. You have data, which will become important for you as students because it allows you to work on real data with real problems. It has machine learning models and weights. It has spaces so you can try things out. So it has a lot of different features that help you in your learning process. Now, how do I easily explain these two next concepts? Yeah. Okay. So attention, it's nothing more than a method or a mechanism in which the model, the machine learning model, weighs input tokens and tries to understand what matters the most the current output is. Self-attention is where that same method, where when it comes from the sequence, it looks at all the other tokens and tries to build context-aware representations. So as a student, we like to highlight the most important lines, before, or, we highlight the most important lines in order to understand, hey, this is what's really important. This is what the professor's going to quiz me on. Now, self-attention would be some type of method where maybe you have the quiz or whatever, and the book would highlight itself, or the book knows what's important. But sometimes you see, like in the beginning of a chapter of a book, it says, "Hey, here's the learning objectives," and at the end it has a summary. Kind of like that, but in text. Um, yeah, that's attention and self-attention. So next slide. Okay, parts of speech tagging. I guess I should have wrote that one out. Speech tagging. That's when we take a sentence or something, and we say, hey, here's an adjective, here's a noun, here's a subject, here's a proper noun. And basically it breaks down a sentence to parts of speech. It's adjective. It's really cool. But that's all that is. Byte pair encoding. So I guess yeah, I have a problem with that eraser today. Okay, so byte pair encoding. We take text and we split it into characters. And then we look at what characters are like right next to each other. And I think I actually have an example that's down a little bit more. I think it uses, maybe your book uses the word lower. They look at every combination or every pair and we try to find ones that are really adjacent to each other. And then we merge them together. So like if we take the quick blah 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 blah. Well, we break this down to T, we break this down to H, we break that down to E, and we do that through the whole dictionary where the word the is very common. Since the word the is very common, we know that these two words naturally pair together. We can merge that into a token, and we can repeat this when we build a vocabulary of common words. Can we do it again and again and again? Okay. How do Legos work? Legos work on the same idea. Legos maybe only have 4 or 5 different blocks, but dude, you can build like a starship and an X-wing and a death ray and like all types of crazy stuff just from a few simple building blocks. That works. Good one. I like that Lego one. Remember that. Oh, okay. Send me, and then there's another one called liminalization. I don't know why it's not on here. I'm going to have another slide for it. Stemming, just there's a couple different types of stemming. And actually, I just looked at, I have this on page 27. But stemming is just getting down to the root of the word, the stem of the word. So all words kind of are similar or match. Because if you have S's and EDs and past tense and present, it can be kind of confusing for a machine. So we stem it and we kind of get down to the root of the word. Emoji handling, that's one of the newer ones, and it's kind of subjective. So if I have emojis, don't want to drop them, don't want to convert them to text, what do I want to do? And this is becoming a bigger and bigger problem because at work I had a nurse that would put emojis in her clinical notes, and it would just mess up the regex, it would mess up the processing, it would mess up everything. And it took me a couple of days to figure out what was causing it not to work. So all you get is this really weird Unicode error. I realized somebody was putting emojis in their clinical notes, and that's what was causing it not to work. So that is one way to kind of think about, hey, if I have a big corpus of text, from 10 years ago, 15 years ago, not a problem. But a big library of text from last year, I could very easily have emojis in it. Condition spell change, there's a bunch of different ways to deal with that. So, when I mentioned bag of words, here is a very simple bag of words. Okay. Let me actually get to the next screen here. There we go. So, um, yeah. So each word is split into its own word. Yes. When it finds a white space, it kind of puts wraps each word by white space. Yeah. Each sentence is split into words, tokens based on white space. Now, as you see, there's some inherent inefficiencies. The word is comes up twice. So we have this duplication, and it's not always the most effective method. Okay. So a vocabulary is created by retaining all the unique words. You can scroll down here so you can see that. There we go. So this vocabulary, in a dictionary, you don't have the same word twice. Just as we don't have the word the twice. Is it the or it is? It is, sorry, my bad. Is. We don't have the word is twice down here in our vocabulary. We got rid of it. Okay, so now that was bag of words, vocabulary tokenization. Now, there's something called word to vec. I'm paying attention to my writing. So let me fix that here real quick. It's funny. 99% sure I fixed that typo. And I don't know because on my screen, it doesn't show up on the PowerPoint, but it shows up on the PDF. Okay, so word to vec, which I think was by Google, 2009, 2010. What it does is, let's talk about the problem. So the issue with bag of words and other things is that we can't really figure out what words are similar and what words are not necessarily similar. Yeah, are these two words likely to be neighbors, yes or no? The word to vec solved that problem. Okay, so we take a word, Richard, and we type misspelling. Vex is another great word. Okay. And then we convert this to a number, a vector, and convert this to a number. In theory, these two should be close to each other. And, we can see that words that share neighbors, coffee, tea, and espresso, end up near each other in the vector space. However, coffee is all one vector, tea is the same vector, and espresso is the same vector as itself. So they share neighbors, and we get context from the neighbors, but we don't keep them together. We don't semantically understand the two. And that's where transformers come in. So let's just kind of stop and think about where we're at real quick because we've covered a lot. So we have text corpus statistic. Now, that is what I'm posting in your discussion, for example. We have metadata, which, for example, on if we look at maybe, I don't know, IMDb, something, whatever, we look at a call, so I look at my AT&T phone logs on my cell phone. We might have the people I called. We might have when I called them. We might have if it's a local or 800 number. Okay. That's metadata related to your call, or not necessarily recording, but that's metadata. Realize I'm looking at the wrong screen here. There we go. Let's see where we at here. Next slide. Okay. So then we have the actual call, the hey, how you doing? Blah blah blah. So that would be this content here. Then we have scores. Now scores can be semantic, or let's do sentiment. Okay. Am I happy or upset during the call? How easy is it to understand the call? Okay. So whenever we get text, these are kind of the things that should be in the back of your mind, the back of your head, saying, "Hey, here's a text coming in. Do I what metadata do I have? What's the scores? Well, sentiment is not always the most accurate. But what about readability? Is it written at like a 15th grade level that nobody can understand, or is it written at a third grade level? Is it generally happy? I love this movie, or is it generally very negative? This was the worst movie ever. So keep that in mind too when you see corpus of text, read text from people, because sometimes the metadata is just as important as the actual context. We have some more terms here, and you know what? Maybe I should just group these all together. Probably the most logical part. So when I talk about noise reduction, I'm talking about cleaning up the cursory text. So I give you a list of all the movie titles in the world. Okay, I need you to maybe remove any HTML tags, and maybe special characters. But noise removal is just a general cleanup thing. That makes sense. Um, Tokenization, breaking text into individual words. We've talked about that. Normalization. Okay, now normalization can be a couple different things. Maybe spell checking, maybe making everything lowercase, maybe removing all the, X, Y, and Z. Stemming can be considered normalization. Now, stemming is a process of reducing words to their root form. So the dog quickly ran. Well, if the dog quick ran, that's the way the machine sees it. We get rid of the ly. And that way we can kind of group all these quicks together and understand that it's an action, it's a motion. Okay. Lemonization and lowercase, maybe once most of this stuff gets, so now stop words. Now, stop words can be a bit of a challenge. And let me explain why. Okay, so at the end of the day, in traditional NLP, we used to remove stop words. And it was thought that stop words are noise. They're just filler context. They're there to, just be filler, right? Noise. I mean, literally, like we saw, that's not necessarily the case. Okay. If we have a lot of stop words, it makes our data set bigger, harder to train, longer to train. So we remove stop words. And in theory, the model understands English better. Because again, the model can now focus on relevant words, okay? But that is not always the case, especially with LLMs now. Stop words. Is there another slide on stop words? There is. Okay. So stop words are commonly used words such as the, is, and. Now, if you took all my slides and removed the, is, and a and other kind of filler words, you can condense my PowerPoint down considerably, and you'd see that words like words effect don't change, reduce noise doesn't change. Okay, useful, and right here, useful, specific application. So we can still get the context of what I'm trying to say. We just are more direct. But there's a problem with that. Okay. Um, and what is the problem? The problem is, in certain subdomains, those words have a lot of power. Pain with fever and pain without fever. If out is one of the stop words, well, everyone has pain with fever. In the legal world, liable for, reliable to. If I remove the stop word to, which is a common stop word, everyone's liable. Not liable for, they're liable to. It completely changes the definition. So it's important to understand that some NLP processes require or remove stop words, some don't. And that for certain domains, it can be very beneficial to remove stop words, and sometimes it's very detrimental. Let me catch my slides up here. Let's see. Remove stop words unnecessary. Okay, there we go. Yep. Yeah, like I said, a lot of LLMs, we don't remove stop words right now as much or if ever. But when we do traditional NLP, we do. Parts of speech tagging. I talked about this a little bit earlier. The best thing to do is show you an example of it. I think, let's see, POS example and LP. Already. The quick brown fox jumps over the lazy dog. So here is a example of POS tagging. Okay, here's actually, there we go. Let's shoot that one. Look at that. Isn't that nice? There we go. So pronoun, verb, noun. That's all parts of speech tagging does. Like I said, there's a couple different ways to do it. But at the end of the day, that's all it is. There's different stemmers, and stemmers are basically kind of like rule-based methods of here, like you see, connected, connecting, connection goes down to connect. Cool, that's exactly what we need. Okay, that is a good example of one. Let me share my screen, yes, and let me move my so I can see the thing too. It does look kind of blurry though, doesn't it? Wait, no, it's just me. Um, but when we go to relational, it goes real, and that's maybe a little too much. But here, relational goes even shorter to REL because TION is something that we remove and AL is something we remove. So the idea of this is to get words kind of the stem, the root, the core of what they are, so the machine can understand them better. And there's different stemmers. Doesn't really matter for this class. Just as long as you know the general concept, you're good to go. but best than I can get. Okay, so what makes LLMs, large language models, so cool? I don't know any other way to explain it. We can take unstructured text, unstructured data, even more important, a picture. We can send it to a large language model, and then we can ask questions about it. We can get summaries from it. We can classify it. We can ask it to draw a picture. I was working with LTX, with video model. Sorry about that. I was working with LTX this weekend, trying to help a friend out. And it's nice because you can take text, like an image to video, image to text, people learn about when you get to diffusion models, and say, hey, I want an educational video of X, Y, and Z, and it generates it. I can take this PDF and take all the text and say, hey, where are misspellings? And hopefully I will find it. LLMs have become powerful not because they can just predict the next word, because they understand, they can make images, they can classify text, they can summarize it, they can do a lot of things. Maybe I should have put this. Maybe that's why. Maybe it's just another picture. If you think about the word bank, um, bank will always have the same vector and word to back. So BERT, or masked word learning, I don't know if that's really a term, but masked language model. The idea is we can teach a model by having a corpus of text, having text and blanking out a word and then having it guess at that word, and then we reward it when it's right. But we find the highest probability. The quick brown jumped over the, we all know what that is, the quick brown fox. Now, it could be anything. The quick brown dog, the quick brown car, the quick brown rabbit. But we've heard that so many times. The quick brown fox jumped. We know what that is. So what if we take a sentence and we mask a word and train them all on and mask another word? That's how we get BERT. That's basic masking. Okay, so we know that we can train a model by masking a sentence. We take a sentence, we cover up a word, we Jeffrey Epstein it and black out a word, we have a machine guess what that word is. That's an encoder only model. That's BERT. But is there another way to do this? What if we just predict the next word? How is weather? We know weather is most likely going to come outside. The stock market went up 50 points today. So we can kind of predict the next word. And this prediction is a decode only, it's a GPT model. It generates one token at a time based on what's before it. And we think about the way that we chat and we do summarization and code. This works very, very well. Where BERT works better at classification, maybe at semantic similarities. So an encoder only model. I have to think of this for a second. We have a bidirectional understanding. We understand the word before it and the kind of after it. The decoder only model, really good at predicting the next word, the next token. Might be the best explanation I've come up with in a long time. Actually, I like the next. Yeah, I do. So how do we train this? We have data, a big corpus of Wikipedia. You can download Wikipedia. It's not that big. Download a book, something else like that. And then you have some type of embedding model, a vectorization. You have something, convert that into a base LLM. You do some base training. And you have a kind of a rough LLM. Maybe a high school student, it would be a good analogy. And what this is just an LLM that can answer basic questions and do basic tasks, but it's not always coherent. It may not be safe. There's a book on how to, I think, create GPT-2. If you want, I can show you some tutorials on how to do it. It's not particularly hard. And it's a great learning experience because it allows you to see what a base LLM is. We take this base LLM and then we find some very maybe specialized data, legal data, medical data, right and wrong answers, morality questions, ethical questions. And we train on that. And we say, hey, okay, this is what you have. Let's kind of fine tune it on this. We iterate until it gets more and more right. As you see with my PowerPoints, I fix them for next semester. I create my PowerPoints, base PowerPoint, and then when I'm going through them with you, I fix them right away. I'm fine tuning them. I think this semester during spring break, I would do a lecture on ethics. But in the interim, hey, remember that never, is it on the next slide? No, it's not. Never share anything with an LLM you don't want shared with the world. We're not sure where an LLM, I don't want to say stopped or starts. So if I have an LLM generate me some song lyrics, it's been trained only on Rihanna music, it's going to create for me something that sounds very much like her. So is that stealing or is that not stealing? Bias and fairness. So if I train a model and incorporate one particular philosophy or idea on it, there could be an inherent bias in it. So those are the major points of responsibility and AI development. And so there's a ton more, which we'll go into on the midterm. Now, in the past, and probably up until this class, most of us have only connected using web interface or a phone. Hey, ChatGPT, what are 10 good places to eat by me? We use a web interface or mobile app. However, in business, we generally more often than not use an API, an application programming interface. And that's basically a code. That's what Open Router is for. Remember, there's a new video on Open Router. But basically, what that allows us to do is programmatically take a request and send it to an LLM, and then programmatically, in theory, get a response back. And we can use command line tools and APIs. Oh. So a while ago, I learned something, kind of very fast. So the iron triangle, cheap, fast, or good. Pick two of them. You can't have all three. You want something cheap and fast? It's not going to be very good. That'd be, an LLM you train. You want it fast and good? It's not going to be cheap. You want it cheap and good? You can probably do that, but it's going to take a really long time to train. So, sure, do I have a picture of iron triangle? I don't. If you look back at or Google the iron triangle, that's literally what it is: cheap, fast, and good. However, when we deal with open source versus closed source software or LLMs, something the idea basically continues through that idea. Well, with open source models, that'd be a lot of the ones coming out of China, Quinn, Chemi, um, ZAI, which generates GLM. We can see all the weights. So we know how they'll respond and when we can see them. Now, in theory, they might not be as capable as closed source models, but then again, they are free. That's where you get that trade-off. And again, how accurate do you need? How good is good enough? And it's something to think about because open source models are becoming a lot more capable, and closed source models are becoming a lot more capable too. It's a never-ending battle. Yeah, so DeepSeek, Llama, which by Meta, other community-driven models, they're fully transparent, they're customizable. There's no vendor lock-in. However, they require a ton of hardware, and they can the out-of-the-box performance varies. We'll say that. Closed source like Anthropic's and ChatGPT's or OpenAI, they're highly tuned for performance. ChatGPT and Claude, the companies want to tune it to be as efficient as possible. We're open source models, so that's a worry. If they're not saving any money by tuning it better. But with a lot of those closed source systems, you don't know how they tune it. You don't get if they update it. If they update it, they might not tell you. I think I made a video on this, but I'm not sure. If not, Llama is a tool. I believe I know I showed Dr. Fonseca it, and I've heard a lot of listeners. It is basically a method where you can, or a program that you can download and run models either locally or remotely. Last year when I did this, it was primarily locally, but now they've really expanded it so you can run models on the cloud. So you can hook up a Llama with Open Router. You kind of have multiple different models you can use, test, and understand how they answer questions differently. An Open Router. So again, this screenshot's from last year because now Claude Sonnet 3.5. I've heard that Claude Sonnet 5 is coming out this week. Here's how fast. In 1 year, we went from 3.5 to 4 to 4.5, and hopefully 5 by this week. But Open Router gives us, and there's a video. I know there's a video on Open Router because I just uploaded it a couple days ago. It's in the help and discussion section. But Open Router allows us a unified, simple way to connect to different, either free or paid LLMs. So we know about all this. Where are we at? Oh, look at that. Under an hour by 3 seconds. Okay, so